you've built your model, trained it on data, but how do you know if it's actually good? This is where model evaluation comes in. It's about objectively assessing your model's performance. And hand in hand with evaluation is understanding overfitting and underfitting, two common pitfalls. First, let's emphasize why we need separate datasets. We typically split our data into a training set to teach the model, a validation set to tune hyperparameters and select the best model during development, and a test set, a completely unseen dataset used only once at the very end to give an unbiased estimate of the model's performance in the real world. Now for metrics. For classification tasks predicting categories, we use metrics like accuracy, correct predictions out of total, precision of what was predicted positive, how many were actually positive, recall of all actual positives, how many were predicted positive, and F1 score, a balance between precision and recall. The confusion matrix is a powerful visual tool for understanding these metrics. For regression tasks predicting continuous values, common metrics include mean absolute error, MAE, mean squared error, MSE, and root mean squared error, RMSE. These quantify the average magnitude of errors between predicted and actual values. Lower values are better for these metrics. Now, let's tackle overfitting and underfitting. Underfitting occurs when your model is too simple to capture the underlying patterns in the data. It performs poorly on both training and test data. Think of it as a student who didn't study enough. Solutions include using a more complex model, adding more features, or reducing regularization. Overfitting is the opposite and often more insidious. It happens when your model learns the training data too well, including the noise and specific quirks, but fails to generalize to new, unseen data. It's like a student who memorized the textbook but can't solve a new problem. The model performs great on training data, but poorly on test data. Solutions include more data, simpler models, regularization, penalizing complexity, or techniques like cross-validation. Balancing bias from underfitting and variance from overfitting is key to building models that perform well in the real world. By understanding these concepts and using appropriate evaluation metrics, you can confidently assess and improve your ML models. Next, we'll look at some foundational ML case studies.